Welcome, future elementary science teachers, to this explainer. I am absolutely thrilled you're here with us because today we're going to tackle something that can honestly feel a little intimidating at first, but is actually incredibly exciting. We are going to learn exactly how to make chemistry totally tangible for your young learners. The goal? Mastering Competency 008F by identifying real-world chemical reactions. We're going to take these big, complex ideas and anchor them right in the daily lives of your students. Ready for this? Let's kick things off with a fast-paced look at chemistry in action. Think about a simple seedling. Watching a plant grow is actually a massive chemical process. It's taking in sunlight, water, and air, and literally outputting physical green leaves and stems. And hey, it's definitely not just plants. Picture kids sprinting across the playground. They're constantly taking in oxygen and food, and their cells are continuously outputting that raw kinetic energy. Next up, combustion. Think about the roaring engine of a school bus. It aggressively takes in liquid fuel and oxygen and violently outputs heat, exhaust, and motion. But, chemistry isn't always fast and loud. Take bridge corrosion. It's the slow, quiet interaction of iron with oxygen and water that outputs rust. It's a powerful degradation process that literally reshapes the structural world around us. And finally, just eating a simple meal. Taking those complex foods in and outputting basic life-sustaining nutrients is a highly complex chemical breakdown all on its own. Every single bite is a reaction waiting to happen. Okay, let's take a breath. So, why did we start with that rapid-fire reaction reel? Well, it all comes down to this fundamental truth. Anchor chemical reactions in real everyday scenarios to establish a true need-to-know context for elementary learners. If you want to really master Competency 008F, this right here is your roadmap. You have to take these everyday events and frame them as clear systems of inputs and outputs. Because when students see that their lunch, the rust on their bike, and the trees outside are all governed by the exact same rules of chemical transformation, chemistry stops being this abstract, boring concept and suddenly becomes a vital tool for understanding their entire world. Section 1. The biological mirror, photosynthesis and cellular respiration. Okay, let's dive into this. Our first paired reactions act as perfect biological opposites. First up is photosynthesis, which is essentially Earth's premium solar-powered chemical reaction. Plants take really simple inorganic components, like carbon dioxide from the air and water from the ground. Then, powered entirely by the sun, this amazing transformation occurs. The plant converts those simple inputs into complex, organic energy in the form of glucose, all while releasing oxygen as a byproduct. Honestly, it's a stunning feat of chemical engineering. Now, let's look at the flip side, cellular respiration. This is how living organisms actually use that energy the plants just stored up. Living things take in that exact glucose and oxygen, and they break it down to release usable chemical energy, which we call ATP. And the resulting outputs? Just water and carbon dioxide. And this brilliantly illustrates the entire cycle. When you show your students these two reactions side by side, the magic becomes so obvious. The inputs of photosynthesis, carbon dioxide and water, are the exact outputs of cellular respiration. And the outputs of photosynthesis, glucose and oxygen, are the exact inputs needed for cellular respiration. It is a perfect, continuous chemical loop. For sure, teaching this mirror relationship is a guaranteed light bulb moment in any classroom. Section 2. Fast and slow breakdown, combustion, and rusting. Let's pivot from biology over to the physical world around us and see how oxygen drives completely different types of reactions. We're going to start with the fast breakdown, combustion, or the burning of fossil fuels. The inputs here are carbon-based fuels and oxygen. And when these react, the mechanics are incredibly rapid and intense. The chemical energy that was stored in the fuel is violently transformed into raw thermal and mechanical energy. Think of the heat and movement of a car engine, along with byproducts like carbon dioxide and water vapor. Now, to teach this effectively, you need the right vocabulary. Combustion is a prime example of an exothermic reaction. Basically, that's a chemical reaction that rapidly reacts with oxygen to transform chemical energy into raw thermal and mechanical energy. Exo meaning out, thermic meaning heat, so energy is exiting the system rapidly. This is an absolutely crucial definition to build into your lesson plans when you're discussing energy transformations. Now contrast that explosive combustion with rusting, which is a slow oxidation process. The inputs are iron, oxygen, and crucially, moisture from the air or water. Over time, these interact to create iron oxide. And here's the kicker. This isn't just iron changing color, it's a completely new degraded substance. The chemical structure has fundamentally transformed. It's literally the exact same oxygen at work here as in our car engine, but with vastly different speeds and structural results. Section 3. Powering Bodies and Tech, Digestion and Chemical Batteries. Moving on to our final conceptual pairing, we're going to connect the digestion of food that fuels our biological systems to the chemical batteries that power all our modern devices. Let's start with digestion. Eating isn't just a physical act. Step 1, the mechanical breakdown, like physically chewing your food, is really just the precursor. All it does is increase the surface area for step 2, deep chemical digestion. This is where the magic really happens, relying on biological catalysts to break the food down until finally, in step 3, those base nutrients can be absorbed by the body. Now, what's really interesting about this slide is the secret weapon behind that chemical breakdown: enzymes. Enzymes are specialized biological catalysts that speed up chemical reactions to break down complex matter into base nutrients. And what's absolutely wild is that they can make these reactions happen millions of times faster than they normally would. Without these biological speed boosters, the chemical reactions of digestion would happen way too slowly to even sustain human life. No way we'd survive without them. Just as we break down food for energy, we engineer devices to do the exact same thing using metals and acids. Chemical batteries follow a really clear path. Step 1, they store potential chemical energy. Step 2 is where the action is. Continuous redox reactions force electrons to move down an output line, and through that movement, step 3 occurs, the transformation into kinetic electrical energy that lights up a flashlight or powers a tablet. It's basically just controlled chemistry in a little metal tube. And tracing that journey from stored potential energy to kinetic electrical energy gives us everything we need to engage our students. Section 4. Crafting your classroom hooks, bringing it back to the elementary learner. Remember, the ultimate goal of mastering Competency 008F is to turn all these concepts into captivating, relatable classroom experiences. You want to ask questions that demand answers. So here's a perfect hook using the photosynthesis input and output cycle. Just ask your students, where does the mass of a huge tree come from if it just drinks water? It's a profound puzzle. It forces them to look at that cycle and realize that the solid mass of the tree is actually built from the invisible carbon dioxide in the air. That is exactly the kind of question that sparks deep, genuine curiosity in a young learner. Or try this one. Tie digestion directly into cellular respiration by asking, how does the food you eat at lunch physically turn into the energy you use at recess? Suddenly, chemistry isn't just something happening in a lab. It's happening right in their stomachs and their muscles. It proves how easily these concepts tie directly into a student's daily routine. We've explored the biological mirror, the fast and slow breakdowns, and the fundamental chemistry of power. You now have the blueprints to anchor these concepts in reality. So I want to leave you with this final, provocative challenge. Which everyday chemical reaction will you use tomorrow to transform your classroom into a living laboratory? The world is absolutely full of chemistry teachers. Go help your students discover it.